Hi everyone, welcome to Education Hub Zone. So today we are going to discuss about physicochemistry. The topic is gaseous state of matter. Before getting started, please don't forget to like, share and subscribe on my YouTube channel. Okay, let's get started. What is matter? Matter is anything that has weight and occupies space. There are four states of matter: gaseous state of matter, liquid state of matter, solid state of matter, and plasma. So in this video we are going to study about gaseous state of matter. Okay, gaseous state of matter. First of all, what is a gas? Gas is a state of matter that has no fixed shape and no fixed volume. Gas is sensitive to volume changes with the change of pressure and temperature. Hence, gas laws come forward. Before moving to the gas laws, let's discuss about measurable properties of a gas. Measurable properties of a gas. Number 1. Mass. By measuring the mass of a given gas, number of moles can be determined by the formula number of moles equals to mass over molar mass. Other formulas of finding number of moles are number of moles equals to number of molecules divided by Avogadro's constant. Another formula, number of moles equals to volume of a gas divided by GMV, which is equals to 22.4 liter. Number 2, volume. Volume of a gas equals to volume of the container in which it is present. The following are the conversions of volume. 1 millimeter cubic equals to 1000 dm cubic, which is equals to 1000 liter. 1 meter cubic equals to 1 million centimeter cubic. 1 dm cubic equals to 1000 centimeter cubic. 1 centimeter cubic equals to 1 milliliter. 1 liter equals to 1000 milliliter. Number 3. Temperature. What is temperature? Temperature is a physical quantity expressing hot and cold. The most commonly used scales are the Celsius scale, formerly called centigrade, denoted by degree capital letter C, Fahrenheit scale, denoted by degree capital letter F, and Kelvin scale, denoted by capital letter K. The Kelvin, small k, is the unit of temperature in the International System of Units, which is measured in the scale of Kelvin. Okay, below is the formula of converting degree centigrade to Kelvin. So the formula says K equals to temperature in degree centigrade plus 273. Number 4. Pressure. SI unit of pressure is Newton per meter square, which is also called Pascal. Other units of pressure are atmosphere, millimeter of mercury, and torr. For conversion, 1 millimeter of mercury equals to 1 torr. 1 atmosphere equals to 101,325 pascals, which is equals to 760 torr equals to 760 millimeter of mercury. Number 5. Density. The SI unit is kilogram per cubic meter. Other units is gram per cubic centimeter. Formula is ρ equals to mass divided by volume, where ρ equals to density, m equals to mass, v equals to volume, relative density, or other word called vapor density. Vapor density equals to molecular weight divided by 2. Okay, now let's move to the gas laws. The gas laws. Number 1. Boyle's law. It said that at a constant temperature, the volume of a given sample of a gas is inversely proportional to pressure. Pressure is inversely proportional to volume. By removing the proportionality sign, we introduce the constant K. So the equation becomes PV equals to K, where K is constant. So if you have two gases, then the equation becomes P1 V1 equals to P2 V2. A. Graph of pressure against volume, inversely proportional. Graph of P against 1 over V, direct proportional. Number 2. Charles' law states that at a constant pressure, the volume of a given amount of a gas is directly proportional to its absolute temperature, V directly proportional to T, where T is absolute temperature, that is, temperature in Kelvin scale. By removing the proportionality symbol, it becomes V over T equals to K, where K is constant. Then the formula is modified into V1 over T1 equals to V2 over T2 for two gases, or V2 over V1 equals to T2 over T1, or V1 T2 equals to V2 T1. Below are the graphs of Charles' law. So the first graph is V against temperature in Kelvin, and the second graph is volume against temperature in degrees centigrade. Number 3. Gay-Lussac's law. It states that at a constant volume, the pressure of a given amount of a gas is directly proportional to its absolute temperature. Pressure direct proportional to temperature. By removing the proportionality symbol, we introduce the constant K. Then the equation is modified into P1 over T1 equals to P2 over T2, or P1 T2 equals to P2 T1, where P is the pressure of a gas, T is the temperature of a gas measured in kelvins, K is constant. The graph of pressure against temperature in Kelvin is a straight line passing through the origin. Number 4. Avogadro's law. In 1812, Avogadro proposed a law so-called Avogadro's law, which stated that at the same temperature and pressure, equal volumes of different gases contain the same number of particles or molecules. Volumes direct proportional to number of moles. By removing the proportionality symbol, we introduce the constant K. So the formula becomes V1 over N1 equals to V2 over N2, where V is the volume of a gas, N is the amount of a substance or number of moles, K is the constant of proportionality at a given temperature and pressure. Number 5. General gas equation. By combining Boyle's law and Charles' law, pressure inversely proportional to volume and volume directly proportional to absolute temperature, we obtain PV equals to KT, where K is constant. So the formula becomes P1 V1 over T1 equals to P2 V2 over T2 for two gases. Number 6. Ideal gas equation. By combining Boyle's law and Charles' law, we obtain PV equals to KT as from the previous general gas equation. With the addition of Avogadro's law, the combined gas law develops into ideal gas law. PV equals to KNT, where N is the number of gas molecules. But since the number of moles determine the number of particles, molecules, then the ideal gas equation becomes PV equals to nRT, where P is the pressure, V is volume, N is the number of moles, R is the universal gas constant, and T is the temperature in Kelvin, that is absolute temperature. Mathematical value of R, universal gas constant, from ideal gas equation PV equals to nRT, taking N equals to 1 mole, temperature equals to 273.15 Kelvin, T equals to 101,325 pascals, V equals to 22.4 times 10 to the power negative 3 meter cubic. We obtain R equals to 8.314 joule per Kelvin per mole, or R equals to 0.08205 liter atmosphere per Kelvin per mole. Density and molar mass of an ideal gas. From ideal gas equation PV equals to nRT, by substituting number of moles equals to mass over molar mass and density equals to mass over volume, we obtain density of an ideal gas. Density equals to molar mass times pressure divided by universal gas constant times absolute temperature, and molar mass of an ideal gas is molar mass equals to universal gas constant times absolute temperature times density divided by pressure, where M is the molar mass. Number 7. Dalton's law of partial pressure states that in a mixture of non-reacting gases, the total pressure exerted is equal to the sum of the partial pressure of the individual gases. That is, total pressure equals to summation of individual partial pressures, or total pressure equals to P1 plus P2 plus P3 up to Pn, where P1, P2 up to Pn represent the partial pressure of each component of a gas. Partial pressure. Partial pressure is the pressure that the gas will exert if it occupies along the total volume of the mixture at the same temperature. Pi, partial pressure, equals to P total, total pressure, times Xi, mole fraction, where Xi is the mole fraction of the each component in the total mixture of n components. Mole fraction, denoted by capital letter X, is the ratio of number of moles of a certain gas to the total number of moles of the mixture of non-reacting gases. Xi mole fraction equals to Ni number of moles of a certain gas divided by N total number of moles of the mixture of gases. The sum of all mole fraction of the gases in the mixture is equal to 1. Application of Dalton's law of partial pressure. To the gas collected over water or any other moderately volatile liquid, the gas collected over water contains water vapor also. Therefore, the total pressure exerted by this moist gas will be equal to the sum of partial pressure, the dry gas, and that of the water vapor. P total equals to P of the gas plus P of the water. Note, P of water vapor, that is, pressure of water vapor, is also called aqueous tension. Number 8. Graham's law of diffusion or effusion. First of all, what is diffusion and what is effusion? Diffusion is the tendency of any substance to spread throughout the space. Effusion is the streaming or escaping of a gas molecule through a small hole. Graham's law of diffusion or effusion states that the rate of diffusion or effusion of a gas is inversely proportional to the square root of its molecular mass. For two gases, gas 1 and gas 2, the formula becomes rate 1 divided by rate 2 equals to square root m2 divided by m1, where rate 1 is the rate of effusion for the first gas, that is volume or number of moles per unit time. Rate 2 is the rate of effusion for the second gas. M1 is the molar mass of gas 1. M2 is the molar mass of gas 2. Note, rate can be defined as volume of a gas diffused per unit time, or number of moles diffused per unit time, or distance per unit time. Kinetic theory of gases. Kinetic theory of gases describes the microscopic model of gases. Postulates of kinetic theory of gases. Number 1. Gases consist of large number of very small particles, atoms, or molecules. Number 2. The volume of gas particles is negligible comparing to the total volume of the gas. Number 3. The molecules of a gas are in continuous random motion. During the motion, they collide with each other and with the wall of the container. Number 4. All collisions between molecules themselves and with the wall of the container are perfectly elastic. Number 5. The pressure of a gas is due to the bombardment of the walls of the container by tiny particles which are in fast motion. Number 6. The molecules don't interact with each other, hence the molecules move independently of each other. That is, no attractive or repulsive force between gas molecules. Number 7. The average kinetic energy of gas particles is proportional to the absolute temperature. The kinetic gas equation is PV equals to nmu square divided by 3, where P is pressure, V is volume, N number of particles, M mass of particles, U root mean square speed of gas molecules. Derivation of kinetic gas equation. Assumption. Number 1. 1/3 of the particles of a gas move along x direction, 1/3 along y direction, and 1/3 along z direction inside the cube with the length L. Number 2. All particles move with the velocity u. Number 3. The bombardment of side A by the particles moving along x direction leads to the force F on the face A. Consequences of the assumptions. Number 1. Each particle has to travel the distance 2L before it hits face A again. Number 2. Since the collisions are perfectly elastic, the velocity will just change from positive u to negative u direction to the collision. Hence, momentum from positive mu to negative mu. Number 3. Change in momentum. Change in momentum equals to positive mu minus negative mu, which is equals to 2 mu. Force due to one particle. F net equals to change in momentum over change in time. From speed equals to change in distance over change in time, but change in distance equals to 2L because the particle will travel a distance of 2L before it hits face A again. Then making subject change in time equals to 2L over ux, speed in x direction. Hence, force becomes F equals to change in momentum over change in time, which is equal to mu square over L for one particle. If there are n particles in the container, n over 3 particle will move to x direction. Number 5. Pressure P equals to force F divided by area A, but area equals to L times L. Pressure equals to force over area, where area is equal to L square equals to nmu square divided by 3V. Hence derived PV equals to nmu square over 3. Note, the kinetic gas equation is derived from a cubic container, but it is valid for any vessel of any shape. Kinetic gas equation in terms of energy. PV equals to 1 over 3 nmu square. PV equals to 2 divided by 2 times 1 over 3 nmu square, where these two will cancel each other, so it doesn't change the meaning of the equation. Then PV equals to 2 over 3 n times 1 over 2 mu square, but a half mu square equals to kinetic energy denoted by capital letter E. Then PV equals to 2 over 3 Ne, where E is kinetic energy, then making E a subject, E equals to 3 PV over 2N kinetic. This is the formula of kinetic energy for each particle. The formula of total kinetic energy is given by E equals to 3 PV over 2. From ideal gas equation, PV equals to nRT, but PV equals to 2 over 3 Ne. Substituting PV by nRT, then the equation becomes 2Ne divided by 3 equals to nRT. Therefore, E equals to 3 nRT divided by 2N. This is the formula of kinetic energy for each molecule, and total kinetic energy is given by the formula E equals to 3 nRT divided by 2. Deduction of gas laws from kinetic gas equation. Number 1. Boyle's law. From kinetic theory of gas, kinetic energy area proportional to absolute temperature. Kinetic energy equals to 1 over 2 nmu square equals to kT, where k is constant. Introducing a fraction of 3 over 3 times a half nmu square equals to kT, where the 3 is gonna cancel itself, so it doesn't change the meaning of the equation. Then it becomes 3 over 2 times 1 over 3 nmu square equals to kT, but 1 over 3 nmu square equals to PV. Then 3 over 2 PV equals to kT. PV equals to 2 kT divided by 3. If T is constant, then PV equals to constant, hence Boyle's law. Number 2. Charles' law. From kinetic theory of gas, kinetic energy is directly proportional to temperature, but kinetic energy equals to 1 over 2 nmu square equals to kT, where k is constant. By introducing a fraction of 3 over 3, it becomes 3 over 2 times 1 over 3 nmu square equals to kT, where the 3 is going to cancel itself, so it doesn't change the meaning of the equation. But 1 over 3 nmu square equals to PV. By substituting it, it becomes 3 over 2 PV equals to kT. Then V over T equals to 2k divided by 3 P. If P is constant, then V over T equals to constant V directly proportional to absolute temperature. Hence Charles' law. Number 3. Gay-Lussac's law. From kinetic theory of gas, kinetic energy is directly proportional to absolute temperature. Kinetic energy equals to 1 over 2 nmu square equals to kT, where k is constant. Introducing a fraction of 3 over 3, it becomes 3 over 2 times 1 over 3 nmu square equals to kT. But the 3 is going to cancel itself, so it doesn't change the meaning of the equation. But 1 over 3 nmu square equals to PV. By substituting it, 3 over 2 PV equals to kT. Then P over T equals to 2k divided by 3V. If V is constant, P over T equals to constant. P is directly proportional to T, absolute temperature. Hence Gay-Lussac's law. Number 4. Avogadro's law. If equal volume of two gases be considered at the same pressure, applying kinetic gas equation for these gases, for gas 1, PV equals to 1 over 3 N1 M1 U1 square. For gas 2, PV equals to 1 over 3 N2 M2 U2 square. Since the volume and pressure of the two gases are equal, then N1 M1 U1 square equals to N2 M2 U2 square. Let's call this equation 1. If the same temperature T is applied for both gases, their mean kinetic energy per molecule will also be the same. Mean kinetic energy of gas 1 equals to mean kinetic energy of gas 2. Then it becomes a half M1 U1 square equals to a half M2 U2 square. The halves are going to cancel each other, then it becomes M1 U1 square equals to M2 U2 square. Let's call this equation 2. Then equation 1 divided by equation 2. N1 M1 U1 square divided by M1 U1 square equals to N2 M2 U2 square divided by M2 U2 square. Then it's going to become N1 equals to N2, hence Avogadro's law. Number 5. Graham's law of diffusion or effusion. Consider two gases, gas 1 and gas 2, at the same pressure and volume, applying kinetic gas equation for these gases. For gas 1, PV equals to 1 over 3 N1 M1 U1 square. For gas 2, PV equals to 1 over 3 N2 M2 U2 square. Therefore, equating the two equations, N1 M1 U1 square equals to N2 M2 U2 square. From Avogadro's law, N1 equals to N2. Then it becomes M1 U1 square equals to M2 U2 square. By rearranging the equation, U1 square divided by U2 square equals to M2 divided by M1. Assumptions. Let small m2 equals to capital M2 and small m1 equals to capital M1, where small m equals to mass and capital letter M equals to molar mass of a given gas. Note, rate of diffusion is proportional to velocity. U1 equals to rate 1 and U2 equals to rate 2, where U is speed. Therefore, rate 1 divided by rate 2 equals to square root of m2 divided by m1, hence Graham's law of diffusion or effusion. Molecular speed. Molecular motions are of three types. A. Root mean square speed, denoted by URMS. URMS equals to 3 PV divided by M, or URMS equals to square root of 3 RT divided by capital letter M, where P is pressure, V is volume, small m equals to mass, R is universal gas constant, T is absolute temperature, and capital letter M is molecular mass. B. Average speed, denoted by UAV, is the average of speeds possessed by molecules in the sample of any gas. Its formula is UAV equals to square root of 8 RT divided by pi m. C. Most probable speed, denoted by UMP. This is the speed possessed by the largest fraction of molecules in a gas sample. Its formula is UMP equals to square root of 2 RT divided by m. Summary. Root mean square speed is greater than average speed, which is greater than most probable speed. Below is the graph of fraction of molecules versus molecular speed. Most probable speed has the largest fraction, then it comes average speed, and the last is root mean square speed. Deviations from ideal behavior. First of all, what is an ideal gas? An ideal gas is a gas that obeys the ideal gas equation PV equals to nRT at all temperature and pressure. It is also known as perfect gas. No gas in nature is ideal. All gases behave ideally at low pressure and high temperature. At high pressure and low temperature, the gases tend to disobey the ideal gas equation, that is, deviate, hence are called real gas or non-ideal gas. Compressibility factor Z. The extent to which a real gas deviates or departs from ideal behavior can be determined by using compressibility factor Z, given by Z equals to PV divided by nRT. Case 1. When Z equals to 1, it means PV divided by nRT equals to 1. Then PV equals to nRT. Therefore, the gas shows an ideal behavior under all temperature and pressure. Case 2. When Z is less than 1, PV value is less than the value of an ideal gas. That is, the gas is more compressible than ideal gas. Therefore, the gas shows negative deviation. Case 3. When Z is greater than 1, PV value is greater than the value of an ideal gas. That is, the gas is less compressible than ideal gas. Therefore, the gas shows positive deviation. Consider the graph below. Interpretation of the graph. Number 1. For hydrogen gas, Z is greater than 1 at all pressure. Number 2. For nitrogen, carbon dioxide, oxygen, and methane, the value of Z is less than 1 at lower pressure and greater than 1 at higher pressure. The dip at the beginning of the curve signifies that the gas can be liquefied. Why some gases shows positive deviations and other gases shows negative deviation? Consider the graph below. For each gas, there is a fixed temperature at which the gas behaves like an ideal gas. The temperature at which a gas behaves like an ideal gas over a wide range of pressure is called Boy's temperature, denoted by Tb. When T is less than Tb, a gas shows negative deviation. When T is greater than Tb, a gas shows positive deviation at all pressure. When T equals to Tb, a gas behaves like an ideal for a wide range of pressure. Causes of deviations from ideal behavior. Validity of the assumptions of deriving kinetic gas equation. Assumption 1. The volume of the molecules in a gas sample is neglected in comparison to the total volume of the gas. At lower pressure and higher temperature, the volume of the gas is much larger as compared to the volume occupied by the molecules. Therefore, the assumption is valid. At higher pressure and low temperature, gas is compressed. The volume of the gas molecules and the volume occupied by the compressed gas become almost of the same order. The volume of molecules cannot be ignored. Therefore, the assumption is no longer remains valid. Assumption 2. No force of attraction between the molecules in a gas. At lower pressure and higher temperature, the volume of the gas is large. Molecules are far apart, hence no attraction. Therefore, the assumption is valid. At higher pressure and low temperature, the volume of the gas is small, compressed state. The gas molecules are closer to each other. Gas molecules develop attractive force. Therefore, the assumption is no longer valid. So, the cause is the gases shows deviation due to the failure of the two assumptions at low temperature and higher pressure conditions. Gas equation for real gases. Van der Waals equation. From Van der Waals in 1873, from ideal gas equation PV equals to nRT, then Van der Waals equation is bracket P plus AN square divided by V square bracket times V minus NB bracket equals to nRT. Volume correction. If B is the volume of a gas molecules, 1 mole of a gas, then for n moles of a gas, the volume equals to NB. Volume correction equals to V minus NB. So from PV equals to nRT, then the equation after volume correction will be P bracket V minus NB bracket equals to nRT. Pressure correction. The pressure of real gas is less than the pressure of ideal gas. P observed equals to capital P minus small p. Then capital letter P equals to P observed plus P, where capital letter P equals to ideal gas pressure, P observed equals to real gas pressure, small letter p equals to pressure due to force of attraction between molecules. Note, small p is direct proportional to concentration of gas molecule square, then P direct proportional to N over V square, P equals to AN square divided by V square, where A is the constant of proportionality. Then by correcting the ideal gas equation, it becomes bracket P capital letter P plus small p times bracket V minus NB bracket equals to nRT. Then the Van der Waals equation becomes P plus AN square divided by V square times bracket V minus NB bracket equals to nRT, where A and V are Van der Waals constant. Critical phenomena and liquefaction of gases. The phenomena of converting a gas into liquid is known as liquefaction. Liquefaction of a gas is achieved by controlling pressure and temperature as follows. Number 1. Increased pressure results in increase in attraction among molecules. Number 2. Decrease in temperature results in decrease in kinetic energy of the molecules. Critical temperature, Tc, is the temperature of a gas above which it cannot be liquefied no matter how great the pressure applied. Tc equals to 8A divided by 27 Rb. Critical pressure, Pc, is the minimum pressure required to liquefy a gas at its critical temperature. Pc equals to A divided by 27B square. Critical volume, Vc, is the volume occupied by 1 mole of a gas at its critical temperature and critical pressure. Vc equals to 3B, where A and B are Van der Waals constant.